Hello, welcome to the video, on a new topic called the distribution and network models. In this particular chapter, we will look at 5 subtopics, which is supply chain models, assignment problem, shortest route problem, maximal flow problem, and 5th, a production and inventory application. Okay, so first, let's start off with the introduction of this chapter. Okay, the distribution and network models. Okay, it is a special type of linear programming models. Okay, so this particular model is what we call a network flow problems. So there are various examples of various situations, that uses the network flow problem. For example, supply chains, transportation, transshipment problems, assignment problems, finding the shortest route problems, and maximal flow problems. So in each case, we present a graphical representation of the problem in the form of a network. I will show you how the problem can be formulated and solved as a linear program. So let's look at the first application, which is on the supply chain models. So what is supply chain? Supply chain describes the set of all interconnected resources involved in producing and distributing a product. It is designed to satisfy customer demand for a product, to be produced at a minimum cost. So those that control the supply chain must make decisions such as where to produce a product and how much should be produced and where it should be sent. We will look at 2 specific types of problems common in supply chains model that can be solved using linear programming. This is the transportation problem. Transportation problems and the transshipment problem. So we have 2 types and I will cover both. So let's first look at the transportation problem. This problem generally arises when we want to plan for the distribution of goods and services from several supply location to several demand location. Typically, the quantity of goods available at each supply location is limited, and the quantity of goods needed at each of the several demand locations or the destination is known. So the usual objective in a transportation problem is to minimize the cost of shipping goods from the origins to the destination. So what we are looking at, we will be looking at minimizing cost of shipping. So what caters a transportation problem? So we have, what we say here, we have the origin, and we have the destination. So origin is what we call the supply location, and the destination is what we call the demand location. So we will have a few supply location or origin, and then we want to deliver goods, to a certain destination. So how? What is the best way? What is the best number of units, that should be transported, from the origin to the destination? So in the transportation problem, it is say here that the demand location is known. So the units, the demand needed here is known. known demand, okay, and the supply here is usually limited. So what is the best way, okay, to maximize, okay, all the delivery of the shipments or the transportation of all the goods, okay, from a limited origin to our destination, okay, at the minimum cost? So let's look at an example. Okay, so let's look at Foster generators. Okay, this problem involves the transportation of a product from 3 plants to 4 distribution centers. Foster Generators operates plants in Cleveland, Bedford, and York. Okay, and then the production capacities over the 3 months planning period for one particular type of generator are as follows. Cleveland can produce 5,000 units, Bedford 6,000 units, and York 2,500 units, making the total production for 3 months at the 3 plant 13,500 units. So then they want to then distribute, okay, the generators through 4 regional distribution centers located in Boston, Chicago, St. Louis, and Lexington. Okay, and the forecasted 3 months demand for the distribution centers are as follows. Okay, Boston 6,000 units, Chicago 4,000 units, St. Louis 2,000 units, Lexington 1,500 units, making, okay, the total demand over the 3 months to be 13,500 units. So what would the management like to do? The management wants to determine how much its production should be shipped from each plant to each distribution center. Okay, how many we want to ship from the 3 plant to the 4 destination. Okay, so here we draw the network graph. Okay, let me open up a slide and we draw the graph together. Okay, let me close this. Keep. Okay, insert a blank slide. Okay, let me do a slideshow again. Okay, so we have just now, as we said, we have 3 origin. So we have origin, okay, 1 which is Cleveland, 2 Bedford, and then 3 is York. Okay, the capacity is 5,000 unit, 6,000 unit, and 2,500 units. Okay, and then the destination, we have 4 destinations. So the first one is Boston at 6,000 units. Number 2, we have Chicago at 4,000 units. And then the third one is St. Louis at 2,000 units. And the 4th destination is Lexington, we have 1,500 units. Okay, so to draw this, okay, we will have our plant or our origin on one side. So let's say we have our plant stroke origin, and then we have our destination, so our distribution center. Okay, so now, so we have 3 origins, so we represent our plant or our origin in circles. Okay, we have 1 Cleveland, 2 Bedford, and 3 York. Okay, we have 4 distribution centers, 4 destination. 1, 2, 3, 4. 1, 2, 3, 4. Okay, and then, okay, for each one of this, we write down our capacity, production capacity on the left hand side. So we have here 5,000, 6,000, and 2,500. And on the right hand side, we write down the demand: 6,000 units, 4,000 units, 2,000 units, and 1,500 units. Okay, so okay, these are known as supplies. These, okay, are our demands. Okay, so this is the origin nodes. Okay, this is the destination nodes. Okay, so this is the distribution or destination nodes. So what we do here is then we will draw out the possible distribution route. So that means plant 1 can deliver to distribution node 1, can go to distribution node 2, to node 3, to node 4. Okay, and then node 2 can go to 1, to 2, to 3, to 4. And then from origin can go to origin 3 can go to distribution node 1, go to distribution node 2, go to distribution node 3, and go to distribution node 4. Okay, unless your problem, okay, tells you that you cannot deliver to a particular area, we will assume, okay, that all the goods from the plant can be transported to a distribution center. Okay, so these lines here are what we call the distribution route. Okay, this is what we call the distribution routes. Okay, one more information that we add on, okay, to this is the cost of transport. Okay, so we will have also add on the transportation cost. So the transportation cost is what we will add on and write it on top of the arrow. So let's say the transportation cost is $3 from plant to distribution center 1. Okay, $2 from plant 1 to distribution center 2, 7 and 6. So you will write it down on the arrow. Okay, so this is the transportation cost that you will write on top of the arrow. Okay, so this is what we call a network graph, a transportation network graph. Okay, a transportation network graph. Okay, if you are asked to draw a transportation network graph, this is what it looks like. Okay, so we have the graph on the right hand side of the slide. Okay, here as I told you earlier, the network graph shows the 12 distribution route, 4 routes for each plant. Okay, so 4 times 3, there are 12 possible routes. Circles are referred to as nodes. Lines connecting to the nodes are what we call the arcs. Note that the direction of flow from origin to destination is indicated by arrows. Okay, it tells you how the transportation will happen from where to where. The amount of the supply is written next to each origin node, and the amount of the demand is written next to the destination node. So this is what they are talking about. Okay, the amount of supply and the amount of demand. Okay, the objective is to determine the routes to be used and the quantity to be shipped via each route that will provide the minimum total transportation cost. Again, determine the routes to be used, quantities to be shipped in order to minimize transportation cost. Okay, then the cost for each unit shipped is then shown on each arcs. Okay, so next what we want to do is to create or to construct our linear programming model. Okay, so how do we write the notation? So if we have here x11, okay, it indicates that the first one is the plant or the origin. Okay, the second number here is your destination. Okay, so when we have x11, it indicates the number of units to be shipped from origin 1, which is Cleveland, to destination 1, which is Boston. x12 indicates the number of units shipped from origin 1 to destination 2, Chicago, and so on. So in general, the decision variables for each transportation problem having m origins and n destinations are written as follows. xi equals to the number of units shipped from origin I to destination j. I think it's missing here a j. Okay, xij is the number of units shipped from origins to destination j. Okay, please add on, yeah? So now, the objective is to minimize the total transportation cost. Okay, so we have transportation cost for Cleveland, from Bedford, and from York, right? We have 3 origin. Okay, and the total cost based on the picture here is, so this is 3x11, 2x12, 7x13, this is 6x14. So we add up all these, we will get the cost of transportation from Cleveland. Okay, so if we look at York, okay, let's look at York. If we look at York, first one is 2, York is 3, so this will be 2x31, correct? This is 5, so this is 5x32, 4x33, and 5x34. So if we add up these 4 routes together, we will get the cost of transportation from York. Okay, so we have that values here. So the sum of these expressions provide the objective function for showing the total transportation cost. So if we want the total transportation cost for Foster, so that would be Cleveland, the cost transportation from Cleveland, plus the transportation cost from Bedford, plus the transportation cost from York. So we add up this together, we will get the total transportation cost. Okay? So, as we know, in each linear programming model, there will be constraints. Okay, so in transportation problems, the constraints are there because each origin has a limited supply and each destination has a fixed or a known demand. So each origin can only they only have available a limited number of goods. Okay, so Cleveland supply, that means from Cleveland to each one of the destination, okay, the number of units sent from Cleveland to each one of the destination must be less than the supplies available, which is 5,000 units. Okay, so this must be less than the availability of supplies or availability of goods. Okay, so that means we have 3 origins, we have 3 constraints. Okay, Cleveland supply, okay, must be less than or equals to 5,000. Bedford supply less than or equals to 6,000. And York supply, when you send out to all the 4 destinations, must be less than or equals to 2,500. Okay. Are there any more constraints? Okay, so there are constraints at the origin. There are also constraints at a destination because the destination has a known demand. Okay, so at the 4 distribution centers, okay, where the demand is known, is fixed, we must meet the demand. Okay, so in the transportation problem, we must meet the demand. We don't send extra. We need to must meet the demand, must meet demand exactly. Okay, so if Boston requires 6,000, we will send 6,000 units. So in a distribution center or in a destination, okay, you can see that you will have an equal sign. Okay, so the goods received, okay, from origin 1, origin 2 and origin 3 must be equals to the demand, which is 6,000. Okay, Chicago is the same. Chicago is the second destination. Okay, so that means the number of units they received from the 3 plants must be equals to their demand, which is 4,000 units. Okay, so recap. Constraints from the supplier. Okay, they have availability supplies. You can take all the supplies or you can take less. Okay, but at the destination, we must meet the demand exactly. Okay, so the equality sign is used here. So when we run the transportation problem through a computer program or computer software, this is a typical computer output, a generic computer output that we can see. So from here, we can see that the optimal objective value is 39,500. That means, what does this tell you? What was the objective? The objective is to minimize the transportation cost. Okay, so therefore we can see that the minimum cost here is $39,500. And what are we doing? Okay, and how is the distribution like? So we can see here there are values in X11, in X12, X22, X23, X24, and X31. Okay, so that means, okay, let me recall what do we have? Okay, so one is plant 1, okay, is Cleveland. Cleveland will send to destination 1, which is Boston, and destination 2, which is Chicago. To Boston, it will send 3,500 units. To Chicago, they will send 1,500 units. Okay. Plant 2, which is Bedford. Okay. As we can see, Bedford sends to 2, 3, and 4. What is 2? 2 is Chicago. 3 is St. Louis. Okay, and then the last one is Lexington. Chicago, they will send 2,500 units. St. Louis, they will send 2,000 units. And then the last one, Lexington, they will send 1,500 units. Okay, and then finally, plant 3. Okay, what is plant 3? Plant 3 is York. York only sends to 1. So 1 is Boston. How many units? 2,500 units. Okay, so then now let's calculate to see if we meet the demand. Oops, here an extra 0 is only 1,500. 3,005 plus 1,500, 345,000. Here we have 2, 4, 5, 6,000. Here we have 2,500. Did we meet the demand? So let's see. 5,000. Did we meet, okay, the supply? 5,000, 6,000, and 2,500. So 5,000, 6,000, and 2,500. Okay, so this is the supplier. Okay, the suppliers have sent out, okay, based on their availability. So if you want to look from the demand side, from the destination side, so we can then see, okay, we look again. Okay, 1, 3,005, and 1, 2,005. Okay, so Boston. So Boston received from Cleveland 3,500 units, and it received from 3 is York, 2,500 units. Okay, second destination is Chicago. Okay, Chicago is 2. Let's see, 2, 1,500, 2, 2,500. Okay, so it received from Bedford 1,500, and it received from 2, 1, 2, and 2, 2. So from Cleveland as well. Okay, wait, let me erase this. Let me rewrite this. Some errors here. Okay, so this is Chicago. Okay, Chicago. Chicago received from Cleveland 1,500, and then from destination 2, which is from origin 2, which is Bedford, 2,500. Okay, destination 3 Okay, we have here 2,000 units. So destination 3 is St. Louis. Okay, St. Louis get 2,000 units from origin 2. Origin 2 is Bedford. Okay, that's all. And then the fourth one, which is Lexington. Okay, Lexington. Destination number 4. So we look at the second number, number 4, which is 1,500 units. Okay, let's do an addition here. 3, 4, 5, 6,000. 2, 3, 4,000. Okay, so the demand at Boston is 6,000, Chicago 4,000, St. Louis 2,000, 1,500. Okay, so the demand at the destination is also met. Okay, so now if you want to calculate, okay, physically the total cost. So we look at the route. Okay, we have already identified the route. Okay, so you can use either this side or this side. We have the route. And then multiply each route by the cost per unit. And we can get that the total transportation cost, okay, is $39,500. Okay, so from here, okay, we can see that, okay, the minimum transportation cost, okay, is $39,500. The values for the decision variables show the optimal amounts to be shipped over each route. So 3,500 units should be shipped from Cleveland to Boston, 1,500 units from Cleveland to Chicago, and so on for the other plants. Okay, so this network, this is the final network that shows you the results, okay, of the transportation problem. Okay, so there are various transportation problem variations. In our example earlier, okay, the problem, okay, we have, okay, the total supply is 13,500 and the total demand is also 13,500. So in our example, okay, in the Foster generators example, okay, we looked at a supply equals to the demand. Okay, a network where the supply is equals to the demand. In cases, okay, if the total supply exceeds the total demand, then no modification in the linear programming formulation is necessary. Okay, so if supply is more than demand, that what it means is that we will have excess supply, extra supply, which will appear as slack in the linear programming solution. Slack for any particular origin, okay, can be interpreted as unused supply or amount not shipped from the origin. So it will stay back in the origin, okay, as inventory, as slack. However, if the total supply, okay, is less than the demand, if total supply is less than the demand, then the linear programming model, okay, of a transportation problem will not have a feasible solution. It's not feasible, okay? I do not have enough goods, okay, to provide for the demand. So in this case, we will then need to modify the network representation by adding a dummy origin with supply equal to the difference between the total demand and the total supply. So with the addition of the dummy origin and an arc from the dummy origin to each destination, the linear programming model will have a feasible solution. Zero cost per unit is assigned to each arc leaving the dummy origin, okay, so that the value of the optimal solution for the revised problem will represent the shipping cost for the units actually shipped. So if zero cost means there will be no shipments made, okay, from the dummy origin. So when the optimal solution is implemented, destinations that have shipments received from the dummy origin will experience a shortfall or unsatisfied demand. Okay? So that means when you draw, okay, you will have, you will have a dummy. Okay, you will have a dummy origin, and anything that goes out of the dummy origin will have zero cost. Okay, but it's still part of your it will still be part of your transportation model, okay, but it will have zero cost. So let's say in the final results, okay, destination 2, okay, so X, let's say for example, the result shows that X42 equals to 2,000 units. So what happens is that, okay, 4 here is a dummy. So that means there will be no delivery of 2,000 units. So destination 2 will experience a shortfall, okay, of 2,000 units. All right. And then second variation, okay, we look at maximization of objective function. So in some transportation problem, the objective is to find a solution that maximizes profit or revenue, okay, per unit as coefficients in the objective function. So if that is the case, then we will solve a maximization rather than a minimization linear programming model. Okay, there will be no effects, okay, to the constraints. So third one, let's say, okay, the linear programming formulation of the transportation problem can also accommodate capacities or minimum quantities for one or more of the routes. So let's say, for example, in the Foster generator problem, okay, let's say from York to Boston, okay, so let's say from York to Boston, okay, let's say from York to Boston, we put there that, you know, the route can only accommodate, or we can only ship 1,000 units between York and Boston. Okay, if we say that York and Boston, we can only have 1,000 units. So in your linear programming model, you have to add on a constraint that X31 must be less than or equals to 1,000. Okay, if, okay, the question tells you, or in the problem, it tells you that there is a limit to the transportation between a particular route, then you will need to write that as one of your constraints. And then finally, okay, establishing a route from every origin to every destination may not be possible. Okay, so let's say, for example, we cannot ship, okay, from Cleveland to St. Louis, okay, because of broken bridge. Okay, because of a broken bridge, there are transportation issues between Cleveland and St. Louis. So if that is the case, then when you are drawing, okay, your network, so Cleveland to St. Louis, so 1 to 3. So I will not draw this arc. I will just drop this arc. Okay, I will take away this arc from the network and everything else maintains the same. Remove the arc, remove the variable, everything else is the same. Okay? So that is transportation problem. And that is transportation problem. So next we look at the second problem of supply chain, which is the transshipment problem. Okay, transshipment problem is actually, okay, an extension, okay, of the transportation problem. Okay, in which you have what we call here the intermediaries node. Okay, what's the difference between transshipment and transportation problem? Is that in transshipment problem we have intermediate nodes, okay, which we call the transshipment nodes. Okay, and it is added to account for locations such as warehouse, okay, somewhere for you to park before you actually bring it to your destination. So shipments may be made between any pair of the 3 general types of nodes. We have the origins, we have the transshipment, and we have the destination. So here we have now origin, transshipment, okay, and your destination nodes. So you have 1, 2, 3. Let's say this is 2 and this is 4. So we can have origin to transshipment. We can have transshipment to destination. Okay, again, supply at the origin is limited. Okay, and the demand at the destination is known, it's fixed. So the objective, we want to look at how many units should be shipped over each arc in the network so that all destination demands are satisfied with the minimum possible transportation cost. So what we do is we will look at an example. Okay, F. Ryan Electronics. Ryan is an electronics company with production facilities in Denver and Atlanta. Okay, so we have production facilities in Denver and Atlanta. Components produced at either facility may be shipped either to the firm's regional warehouses, okay, which are located in Kansas City and Louisville. So we have warehouse, which is Kansas City and Louisville. And from there, okay, firm supplies retail outlets in Detroit, Miami, Dallas, and New Orleans. Okay, so then they have the retail, okay, which is the final destination at Detroit, Miami, Dallas, and New Orleans. Okay, so in the transshipment network graph, you will see the same thing. The concept is still the same. Okay, we have the limited capacity, limited supplies, written on the left hand side of the origin. Okay, the demand written on the right hand side of the destination node. Okay, then we have arcs showing the distribution routes, and we have, okay, the cost, okay, of shipments written on top of the arcs. So we need a constraint for each node and a variable for each arc. So let Xij denote the number of units shipped from node I to node J. So you can see here in a transshipment problem, okay, sorry, your I and J is no longer, we can no longer denote I as origin, J as destination, because here we have a transshipment nodes. So in a transshipment problem, we can see that the nodes are now numbered numerically in an ascending order. Okay, you start off with the smallest, 1, 2, okay, then 3, 4, and the transshipment nodes destination is 5, 6, 7, and 8. Okay, so now your Xij could be, let's say, X13 denoting plants to warehouse, denoting Denver to Kansas City, or it could be X42, okay, denoting the route between the warehouse in Louisville to the retail outlet in Miami. Okay, so here, take note of the numbering of your nodes. Okay, so it is now numbered in a numerical order depending on the number of nodes. So if you have 10 nodes, then you will have node 1 to node 10. Okay, so looking at this, okay, because the supply at the Denver plant, okay, is 600 units, the amount shipped from Denver plant must be less than or equals to 600. If you have 600, you can only send out at the most 600 or anything less than that. So mathematically, it is written as X13 plus X14 equals to 600. So this is X13. This is X14. So Atlanta is the same. Atlanta have 2 nodes, 2 routes. So we have X23 and X24. Okay, add up together must be less than or equals to 400, which is the available supplies here. Okay, now let's look at node 3. Okay, this is where it is different. Okay, node 1 and 2 are very similar. It's just that you have to take note of the numbering. But now node 3 is a little bit different. Because in node 3, okay, it doesn't have its own production supplies. And it doesn't need any demand as well. Okay, so what we are going to look at is that the number shipped in, okay, to the warehouse must be equals to the number shipped out of the warehouse. Okay, if I ship in 1,000 units, regardless, okay, of the original plant it comes from, I must ship out only that amount of units. Okay, so here, if we look at shipping out, okay, this is out. So we have X35 plus X36 plus X37 plus X38, okay, must be equals to X coming in, X12 and X13 and X23. Okay, so in a transshipment problem, okay, usually the most common way to write it is we want it to be equals to 0 on the right hand side. So we bring, okay, the in shipment to the left hand side, the number of units, so it becomes negative X13, negative X12. Okay, so this indicates the in shipment, this indicates the out of the warehouse shipment. Okay, for note 4, so we can see that this is in and this is out. Okay, and then the demand is the same way as how we wrote the transportation, what comes in. So this is coming in from 3, so x35. This is coming from 4, x45. Okay, must be equals to the demand. Okay, this is the fixed demand that you get here. Okay, so as usual, the objective function reflects the total shipping cost over the 12 shipping routes. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so that makes your linear programming model. Okay, so this is your linear programming model. So we have our original nodes. Okay, take note. Less than or equals to inequality. Our transshipment node equals to 0. Okay, we have our in. And then we have our out shipment. Okay, and then we have our destination equals to the number of nodes demanded. And then remember our non-negativity. Xij must be greater than or equals to 0 for all values of I and j. Okay, so then if we were to run this particular model through a computer software, this is a generic output that we can observe. Okay, so from here we can see that the optimal objective value is 5,200. So meaning that, okay, the minimum cost is 5,200 ringgit or $5,200. And the shipping arrangement is as such. So you take note of how it is being shipped. Okay, in and out. Okay, so if I were to write it down in a table, okay, the route will be from Denver to Kansas to Louisville, Atlanta to Louisville, Kansas City to Detroit and Dallas, Louisville to Miami and New Orleans. Okay, from the unit shape, from the cost per unit, we can see that the total cost is $5,200, which tallies with what we can see here, okay, in the objective function. Okay, so for an illustration of a more general type of transshipment problem, let us modify the Ryan Electronics problem. Now, suppose that it is possible to ship directly from Atlanta to New Orleans at $4 per unit and from Dallas to New Orleans, okay, at $1 per unit. So now we added two new paths, two new routes. Atlanta straight to New Orleans, okay, at $4 per unit. And then the second route is from Dallas to New Orleans at $1 per unit. Okay, so now we must add this, okay, into our linear programming model. So we have new variables, x28, right? This is x28, and we also have a new route, so a new variable x7 and 8. Okay, so we can see the change. Okay, we now have x28, x78 up here in the objective function, as well as okay, in our linear programming model. In our constraints, okay, that involves, okay, node 2, which is from Atlanta, and node 7 from Denver. So our nodes that will be affected when you rewrite your linear programming model will be this one, and this one. Okay, so we can see here 2, 7, and 8. So if we do that, we can now see that if you are to run the linear programming model, the value of the optimal solution has now been reduced, okay, by $600 when we allow the additional shipping routes. Okay, the value of X28 equals to 300, indicating that we are sending 300 units directly from Atlanta to New Orleans. Okay, the other route we added is X78 is 0, so no units were actually shipped between Dallas and New Orleans in this particular problem. Okay, the same thing. Okay, there are also transshipment problem variations. Okay, and these variations are very similar to what we have discussed earlier for the transportation problem. Okay, but when we add one or more constraints of the form Xij is less than or equals to Lij to show that the route from node I to node J has a capacity of L, we refer to the transshipment problem as a capacitated transshipment problem. Okay, that means that I say that from Denver, okay, to Kansas, limited units, let's say limited units is 200 is 400. So that means you have to add on, okay, Denver to Kansas is X13 must be less than or equals to 400. Okay, so this gives you what it says, that if you have this, then this becomes a capacitated transshipment problem. Okay, we put a limit, okay, to the number of units that can be shipped between routes. This becomes a capacitated transshipment problem. Okay, I will stop the video recording here for the first part, okay, of the distribution and network models. Okay, we will continue the second part in our next class, okay, to finish off the chapter. That's all. Thank you for watching. Bye.